Hi everyone. Continuing the last class where we discussed the concept of edge connectivity, vertex connectivity, and cut edge, cut vertices for a simple graph or for a graph. Now, let us try to find out these things for some spatial graph. Like a spatial graph, when I'm talking about it is wheel graph, it is cycle graph, it is complete graph, complete bipartite graph, regular graph, and all. So let us start the discussion. First, try to find it for Cn. Cn is a cycle graph. As the definition says that Cn is a cycle graph which is having at least three vertices and every conjugative vertex is connected to its precedent vertices as well as successor vertices. For example, if I write C3, because minimum vertices is 3, so it should have 3 vertices. Let us name as V1, V2, V3. So V1 is connected to V2, V2 is connected to V3, and V3 is connected to V1. Here, conjugative vertices are connected to each other, so we call it as a cycle graph having three vertices. Okay, so this is our C3. In the same manner, if I talk about C4, so C4 is having four vertices. So C4 is having four vertices with the same condition that conjugative vertices are connected to each other. So C4 looks like this is one vertex, this is second, this is third, this is fourth. Let us give the name as V1, V2, V3, V4. So this is how C4 will looks like. As already discussed that the shape of the graph does not matter. What exactly matter the connections. If two graphs is having the same connections, we call them as the identical graph. This we call as C4. One more, let us try to draw C5. That is a graph which is having five vertices and conjugative adjacent vertices are connected to each other. So V1, then V2, then V3, then V4, then V5. We call this graph as C5. Now, let us try to find these parameters. So, which are what? The first one, we are having cut edge. Then we will talk about cut vertex. Then is edge connectivity. And then vertex connectivity. These are the four results or parameter related to the connected graph. So cut edge for the first graph. If you see, if I remove edge between B2, B3 or B1, B2 or B1, B3, the graph is still not disconnected. Like if I remove edge B2, B3, this is removed, still we can move from anywhere to anywhere. So single edge removal is not there to make the graph disconnected. Talking about cut vertex, it is also does not exist. If I remove the vertex V1, the leftover part, which is looks like B2 and B3, is still connected. If I remove the vertex V2, only V3 is left. So one vertex removal is not making the graph disconnected. In this, what I did, I removed two vertices. So for this cut vertex also not exist. Talking about the connectivity part, so edge connectivity, if I remove any two opposite edges, the graph comes out disconnected. Like if I remove these two edges, the graph looks like this. So B2 got disconnected from the leftover part and it is minimum because by 1 it is not happening, by 2 it happens. So edge connectivity for this graph is 2. The same manner, vertex connectivity, if you see this one, the first one I remove V1, so this is what obtained. When I remove V2, this is what obtained. So the second definition that we discussed in the last class, vertex connectivity, either the graph comes out as disconnected or it removed into a single vertex graph. So over here, you can see the graph is reduced into a single vertex graph. So the vertex connectivity is 2. In the same manner for C4, vertex connectivity and edge connectivity does not exist. Vertex connectivity is 2. If I remove opposite two vertices, what left? V1, V3, disconnected. So vertex connectivity to edge connectivity. In the same manner, remove the opposite edges. So C4 is also having the same result as C3. The same for C5. So in general, we can say in cycle graph CN, cut edge and cut vertex will never exist, and edge connectivity and vertex connectivity is always true. Whether it is C3, C4, C5, or we can take any N. So this is for CN. Talking about the second special graph, which is WN, also known as the wheel graph. Wheel graph is the extension of a cycle graph. Wheel graph is the extension of a cycle graph. We can relate it like a wheel. Cycle graph is only circumference part. If we include one vertex at the center and connect it with all other vertices on the circumference, we obtain a wheel graph. For example, this C3 is converted into a wheel graph if I add one vertex at the center and connect all the vertices which is there at the circumference with this vertex. Let us see how. So this is your C3 as we already draw it. This is our C3 that we already draw it. Now I am going to put one vertex at the center and will connect it with all the vertices which is there on the circumference. So this is the new vertex. Earlier it is having V1, V2, V3. I included one more. We will call it as V4. So this is your V4. So this we called as a wheel graph. Since it is the extension of C3, so the name will be W3, even though it is having four vertices. So in general, we can say in Wn, the number of vertices is always n plus 1. In Wn, the number of vertices is n plus 1. Similarly, for C4 can be converted into W4 if I added one vertex at the center and it looks like this. We call it now as W4. In the same manner for C5, just include one at the center and this is how it will looks like. We call it as W5. Okay, talking about the connectivity part, cut edge and cut vertex will also not exist in a wheel graph. Cut edge, we can say not exist. Cut vertex, we can say not exist. But edge connectivity and vertex connectivity is there, which is 3 in both the cases. So we can do verify for it. If I remove all the edges which is connected to V1, then this vertex V1 comes out disconnected from the leftover part. So minimum is 3. By 2 it can't be done. You can remove any two edges from the graph. The graph is still connected. For vertex connectivity, if I remove V2, the graph part is still connected. If I remove V1 is still connected. V3. Now the graph reduced into single vertex graph. The definition point. Either disconnected or remove into single vertex graph. So here it reduced it to single vertex graph. So that's why three vertices are supposed to be removed. So in WN, these are the result related to the connectivity. Cut vertex, cut edge does not exist. Edge connectivity, vertex connectivities exist, and it is 3 over here. Talking about the next spatial graph that we are having as KMN, called as a complete bipartite graph. Like we can have K1, 2 with the condition that M is always less than equals to N. K12, how K12 looks like? There are two partitions. One partition is having one vertex, let it be A. Second partition is having two vertex, let it be B and C. And every vertex of the first partition is connected to every vertex of the second partition. If this condition holds, we call this graph as complete bipartite graph. So this is your K12. We will call this graph as K12. In the same manner, if we are talking about K22, so K22 means what? Partition having two vertices. and all the vertices of opposite partitions are connected to each other. So this is how a graph K22 looks like. We can give the name as A, B, C, and D. If I want to draw K2, 3, so first is having two vertices, second is having three vertices. A complete bipartite graph definition says that every vertex of the first partition is connected to every vertex of the second partition. So this we call as K23. This we call as K23. In the same manner, we can draw K11 also. So this is K11. Both the partition is having only one vertex. Talking about the connectivity part. So K11, in K11, if I am talking about K11, or when M is equal to 1, better to say, like K11, K12, K13, K14 kind of scenario. In that case, the cut edge and cut vertex is like over here. If I remove this edge, this part B will become disconnected. If I give the name as even, so even is the cut vertex. Cut edge. And we are removing edge. On the same side, if I remove this vertex A, the leftover part is B, C. Looks like that, disconnected. So we can call A as the cut vertex of K12. The condition when M and N are more than 1. The condition when M and N are greater equals to 2. I'm talking about both, at least 2. In that case, cut edge and cut vertex does not exist. Then what comes in the picture that we called as the edge connectivity and vertex connectivity. Edge connectivity and vertex connectivity in that case. So for that, what we can do, let us try to see that also. So for that, the connectivity will be what? Just try to understand the definition point of view. Out of M and N, M is the smaller one, and that these M vertices are connected to all N vertices of the second partition. And in the second partition, all N vertices are connected to N M partition, M vertices of the first partition. And M is the smaller one. M is the smaller one. So the edge connectivity for this is M. That means over here, if I remove these three edges, you can see this A becomes disconnected. This A becomes disconnected. But on the same time, in place of 3, if I remove these two edges, first is this, C is become disconnected from the graph. That means what? In K23, by removing 3 edge, the graph also become disconnected. By 2, it is also disconnected. By removing 1, it is not disconnected. So the minimum one is 2, which is minimum of 2 and 3. So in KMN, edge connectivity as well as vertex connectivity is always M and N when M and N are greater equals to 2. Cut edge, cut vertex will not exist in this case. Will not exist in this case. But if there are other condition like K11 or K12, then cut edge and cut vertex will also exist. So this is the general result for a complete bipartite graph. Edge and vertex connectivity is always the minimum out of M and N, which is M. And M and N, if any one of them is 1, then in that case we can say cut edge and cut vertex exist, otherwise not. Otherwise not. In the same manner, you can verify result for Kn, which is a complete graph. So in complete graph, we can say cut vertex connectivity and edge connectivity is 1, n minus 1. Vertex connectivity and edge connectivity is n minus 1 in case of complete graph. In the same manner, you can think on this concept for regular graph or for some other general graphs, like some shapes are given, we are able to find, or the question is asking for the connectivity point of view, we can use this concept to find it out same. I hope you understand the concept. It is suggested to practice these problems or some more problem to get it detailed knowledge about the connectivity. Now closing the session.